Hello everyone and welcome. Today my name is Anthony Shivkumar from Anshiv Robotics, and today we're going to dive deep into topics that is absolutely critical for high performance AI but is often overlooked. And today we're going to talk about the advanced memory strategies for CPUs. And what we'll cover today are powerful in-depth techniques for designing memory layouts. But I want to be clear from the start, this is a huge subject. And even with the details we'll get into, we are only touching the surface. There will always be more to explore, and we may revisit this with even more advanced concepts in the future while we start to implement the AI, especially the transformer algorithm using HPC techniques from the grounds up. And then we'll come back to this advanced memory layout and fine tune some of those concepts. So this is just kind of like more of an introductory, but still it's got a lot of depth into it. So the primary goal of this video is to give you a game plan, a strategic framework for how to design your models. For too long, we've been encouraged to be creative and design data structures without fully understanding the profound hardware implications. And this often leads us to inefficient models that hit performance walls, especially when we're dealing with an algorithm that is compute intensive and requires performance for it to be useful in some shape or form. And so today we're going to try to kind of like, change that a little bit. What we will do is establish clear boundaries to work within. These aren't some random limitations. They are powerful principles derived from how CPUs actually work. So we're going to design our algorithms for the CPU. And by understanding and respecting these boundaries, we can work towards our ultimate goal, which is making the AI more powerful, more accessible, and much more easy to use on your on CPUs. And for that, we need to get the memory structure, the data layout, the execution flow, and how all your pointers will work together is genuinely challenging and frankly rarely taught. And by the end of our session, I hope you'll see that by mastering these details, anyone can confidently design state-of-the-art language from first principles, especially C. C should be actually renamed as the first principle language with ease. And the final and crucial point, by following this methodical approach of using a single contiguous memory block, we create an environment where memory boundaries are incredibly well defined. So we're not just going to create, memory and figure out, and have things like buffer overflows. I mean, you could, but because we know our boundaries, we know our offset, we can create test scripts to make sure that you're safe within those memory pointers. And this not only boosts performance, but also drastically helps prevent common issues like, as I mentioned, buffer overflows and memory corruption, making it far easier to write robust test cases to protect against any memory faults. So let's get started. Alright, so this slide is our game plan for today. I call it the memory optimization pipeline because it's not just a collection of random tips, it's a coherent strategy where each stage logically builds on one before it, taking us from a basic solid foundation to a highly optimized hardware-aware design. And in the first part, we are going to be talking about the prevent interleaving. And the core idea is simple. We must store our data in the exact order it's going to be executed. So we do this by organizing memory layout to match our access pattern, which gets rid of random pointers chasing and enables the CPU's L1 and L2 cache prefetchers to work perfectly. Next, we look at SNC, which is kind of a sub-NUMA clustering, which is where every core of your, we're talking about server-grade CPUs specifically, where you have multiple DRAM channels, and each DRAM channel is generally associated with a specific core. So you want to put your data in that particular DRAM so that it's faster. It's much more easily accessible with some higher speeds for that particular core. And how we do this from two levels, where we still have this continuous memory block, but during runtime we're able to tell that this block of code should be stored in this block of data should be stored in this DRAM, and this block of code should be stored in this DRAM, and things like that. So that's what the the sub-NUMA clustering is. And this is a powerful feature of modern Xeon CPUs that creates these logical NUMA nodes right out of the L3 cache slices. And the main benefit is that it reduces the chatter across core cache snooping and improves latency for local memory access. And that leads us directly to stage 3, which is the NUMA awareness. And this is mostly when you have a dual chip, triple chip or dual socket configuration on your motherboard, and it's basically if you have a neighboring chip. This is about the entire system. Memory graph geography matters deeply, especially on servers with multiple CPUs. We'll talk about how to split our contiguous data blocks into NUMA specific regions using mbind, and then lock our processing threads to those local cores using pthread, set affinity and number of processors. I've already done this video on one of my HPC videos before, so have a look at that. Links to those will be in the description below, where I actually physically write the whole C code, and we have a dual socket C system that I kind of like written code of how we can split data and split computation between dual sockets, and this takes care of that NUMA awareness, which is known as non-uniform memory access. And in stage 4, we will cover cache lines alignment. This is absolutely critical for multi-threaded workloads, padding our token embeddings to 64-byte boundaries. We prevent them from crossing cache boundaries, which eliminates false sharing. A scenario where multiple cores accidentally fight over the same line of cache, killing us scaling. So we won't be talking too much about this because I've already spoken quite a bit in my previous video about this, but there is few things that I kind of like missed over there, especially when it comes to alignment between tokens. And we may just touch on the at the surface level in today's presentation, but a lot of it is going to be focused on the prevent interleaving, as that's the most kind of the most complex part of this whole process of memory. And once we're scaling, we can fine tune with stage 5, which is known as the prefetching pipeline. This is where we manually tell the CPUs what data we'll need next. Instructions like prefetch. The goal is to overlap our computation with memory latency so that the powerful AVX instructions and the diffuse multiply and add units are never sitting idle when waiting for data. And finally, all of this will come together on our memory flow strategy. We learn to treat the entire memory access process itself like an instruction pipeline. We predict what we need, we prefetch it, we compute on it, and then we write it back. And this is what ensures a smooth continuous throughput by keeping all parts of the CPU active and productive. So that's the pipeline. As you can see, it's a logical progression from the grounds up with the roadmap in mind. So let's dive into the first part. The core problem and the choice. Alright, so let's kick things off with part 1. In this section, we're going to lay the foundation for everything that follows. We're going to talk about a single fundamental decision that every AI developer makes, whether they know it or not. And this is the core problem and the choice. The choice is, how do you decide to lay out your model's data in memory? And as we're about to see, this single decision has massive cascading effects on performance. Now, of course, people are writing at the high level in Python and stuff may not necessarily look at these details, but the developers and engineers who are working on the Intel 1 API or the CUDA binary itself, absolutely have to consider all of these things, whether it's a GPU or a CPU, dealing with memory access for that speed that they're all trying to sell. So here is the 2 fundamental approaches to memory allocation for a transform model. Now, on the left, I also want to make sure that I'm taking a snippet from a lot of Karapathy's code from a C LLM underscore GPT2.c, and we're just kind of like breaking that part a little bit, and not because he's absolutely fantastic, highly recommend follow everything that he does. This is more about high performance compute. All of what I'm trying to showcase is showing that you can do many of these things by just tweaking and improving on the shoulders of giants, in this particular case Karapathy's work, to kind of like clean that up a little bit so that you can make it performant on CPUs. And there's certain details that generally for the broader audience may not necessarily be fun or exciting, but those details matter when we're talking about performance, especially when we're dealing with an algorithm like modern AI that is extremely compute intensive, and the compute that is required to process them in a much more usable manner requires high performance compute principles so that you can use them. And that's where I'm coming from. So on the left, we might have this Block-per-Tensor structure. Now you might recognize this from a popular C implementation, and all similar tensors are grouped together. So we have all the QKVs, the query key and value weights for all layers are in one big block. All the multi-layer perceptron are all in one big block, right? And all the layer norms are all in one big block. So the main advantage is that it's fairly simple to manage the pointers, right? So it's very simple to manage because even all the layers and everything is all part of this one block. The disadvantage is a performance disaster for processing a single layer, as we'll see. Now on the right, the layer by layer allocation. Here all the data for a single layer, its weights, its activation, everything is grouped together in one contiguous block. This is designed to give us incredible cache locality, which is the key to performance. This is the core architecture choice we're making right at the beginning. So now let's look at the poor cache utilization on the left. When the CPU needs just a few bytes for the QKV, it's forced by the hardware to load an entire 64-byte cache line. But because the next piece of data it needs is in a completely different memory region, the other 56 bytes in that cache line are effectively wasted. This is cache waste, and it absolutely kills your memory bandwidth and efficiency. So that's what's happening, because you might need something from this particular block, you need something from this computer block, this from this computer block, and eventually, and then you're also loading all the layers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in some shape or form, but all you're processing is layer 0 first. Layer 1 cannot be processed, all the computation of layer 1 cannot be processed before layer 0. But now layer 0 is completely fragmented into different multiple memory regions. And even though it's all contiguous blocks, because it's fragmented, the cache lines, you're going to have a lot of cache misses. So this might, not have proper cache utilization, and you'll have cache eviction, and you'll be just wasting clock cycles in just terms of, just getting memory to the compute nodes in order for them to compute just matmul operations. That's why memory is important. Now let's look at the excellent cache utilization on the right. Because all the data for layer 5 is contiguous, now we put all the data for layer 0 is 1, all the data of layer 1, it's all in one contiguous block. When the CPU loads a cache line, it's extremely likely to use all of the data in it. There's no waste. The simple principle is the secret to achieving a good high efficiency. And now because it's going to be sequential for layer 1, it's going to process the QKV, it's going to perform the layer norm, it's going to perform the activation, it's going to perform the multi-layer perceptron, it's going to perform the activation, and then then that will be feeding this output will be now fed to the input of layer 5, and you go on and on and on. And because it's sequential, you can only perform layer 1 if layer 0 is computed. You can only perform layer 5 if layer 4 is computed, because the output of layer 4 is the input for layer 5, and things like that. So you can't skip a layer in order to process something ahead. Now the computations within each layer, the matmul operations are all parallel, but the layer itself is sequential. And understanding this concept of cache utilization is fundamental to writing any kind of high performance code. If this is starting to click for you, maybe take a quick second to hit that like button and subscribe for more deep dives like this. It really helps the channel out and let me know that you're finding this valuable. So now let's look at the bottom section with the blocks-per-tensor approach to process a single layer. The CPU has to jump all over main memory. So we just have a look at this first, the memory over here. And it needs to grab, say, the QKV. In this particular case, how does the cache hierarchy work in a CPU? We go from L3 cache, we pull up all the data, it goes to L2 cache, which is now, this is shared across all the cores. Then it goes to L2 cache, which is now per core, and then you go to L1 cache, which is again per core. So it's 2 MB, 32 KB, and then here we have probably 512 bytes, which is around 64. 512 bits, which is around 64 bytes. So the CPU is processing things in bits and bytes over here. So everything over here is all about how much memory we can squeeze into each one of them, and how quickly and accessible can you make that memory and data, so that it's not wasting time fetching and storing and finding. The more streamlined it is, the faster the processing is going to go from L3, L2, L1 compute store, L3, L2, L1 compute store, things like that. So that's what we're trying to aim over here. So with the block-per-tensor approach, to process a single layer, the CPU has to jump all over main memory, and this is what we're trying to show over here. It's going to jump all over main memory, because all the QKV waits, and after QKV waits for that particular layer, then it has to go to another block of memory for multiple layer perceptron. Then it needs to go for another layer for all the layer norm. And then each jump has a potential cache miss, which stalls the CPU while it waits for data from a slow RAM. This is why it results in high cache misses. Now, in contrast, our optimized layer-by-layer approach ensures that all data is sequential. The CPU can just march through a single block of memory, which leads to very few cache misses and massive performance gains. And that's what we're trying to aim over here, is can we increase the cache utilization and make sure that the data is constantly, that is required for the next computation is efficiently loaded into the caches, so that the CPU is not idling and stalling. So in part 1, we established the two main choices for memory layout. Now, in part 2, we're going to go to look at the real tangible consequences of making the wrong choices. This isn't just a theoretical exercise. The performance difference is massive, and it all comes down to how well we align our software design with the realities of the underlying hardware. So now this chart says it all. It compares the performance of the traditional Karapati type layout in red against our optimized layout in green. And now across the main stages of transformers. Now I'm going to show you where the differences when we really go deep into each part of the algorithm to know where this actually can cause major hits, especially when it comes to getting that data into the computation, into the execution units of the CPU, where they actually perform these maximal operations. So the performance starts, they're okay with layer norm because there's not much to compute during the layer norm. But then it falls off the cliff. The performance degrades with each subsequent operation. So then we go to QKV, and the QKV, it requires a lot more data from all different parts of memory region. So to perform the query, the key, the value, and all the other parameters that it needs to fetch from memory to a point where it can cause some issues that we will explain exactly why and where. Because as noted at the bottom, each operation adds more concurrent memory streams, and the hardware stream tracker gets completely overwhelmed. So we're going to talk about something as a stream tracker, which means that, say we're doing maximal operations of A and B. So, the matrix operation of A is going to fetch, say, from one part of a data. Matrix operation of B is going to fetch from another data, and they both can be prefetched. The CPU is smart enough to know that they're coming from different regions, and you can prefetch it. Now, what happens if you have C, and you have D, then you have E, then you have F? There's only so much prefetchers it can use. And that's why we talk about stream trackers. So the more streams that you have that are not in contagious memory blocks, and it's not able to methodically find proper offsets, because a prefetcher can understand a memory offset, and if it's constantly bouncing around in memory, you'll realize as it's going across the computation, the prefetchers are going to be overwhelmed, and to a point where you're not utilizing them properly, and then you'll have degradation because now the prefetcher is not able to predict where exactly in memory is the next computation required. And I mark the QKV as a tipping point here because this is where the hardware prefetcher's its confidence completely collapses. In stark contrast, our layout maintains a consistent high performance throughput because our slab layout prevents this entire cascade of failure by processing one tensor type at a time. So let's break down exactly what that stream explosion looks like. Now this slide shows the cause of the performance degradation we just saw on the graph. On the left, you can see the traditional layout in action. For layer norm, it's manageable with 3 active memory streams. So you have the input, you have the you'll have things like the embedding dimensions and the context length of your AI in some shape or form, and this performing a simple the input minus mean multiplied by the standard deviation, reciprocal standard deviation multiplied by the gamma and the beta, and these are all arrays stored as an output. So you can say there are few streams over here in some shape or form, so it's around 3-4, and it's still manageable because I think in modern Xeons you have 6 to 8 if I'm not mistaken. You'll have to look at the data sheets, but you can say this is a safe computation, that it's good, nothing is wrong. You can have 4 different memory regions, and the AI is and the CPU is smart enough to know exactly how to kind of fetch that data in a very sequential manner. But then you hit the QKV, and QKV, the attention, and suddenly the CPU is trying to read and write from many different types of memory locations at once. It has to read the input weights, it has to read the query, the key, the values, the output, and now we're starting to look at that every one of this, and then it needs to require the attention weights. It's starting to become a little bit more overwhelming for the CPU, and this starts to become kind of like a disaster, because now the prefetcher, which might only be designed to track say 4 streams, is now simply giving up, which means now you're going to have cache evictions, and then from that cache evictions you're going to use clock cycles, you're going to waste time, and to a point it's just going to be slower and slower and slower. And that's why a good memory layout allows us to minimize these streams, because once we know the offsets are very much predictable, and a CPU has a very simple predictable algorithm within it so that it can access memory as quickly as possible. So our goal is to make our data fit in a way that the CPU can predict the next access to that data. But if they're all jumping everywhere and it's not a clean offset and it's constantly moving around, there's going to be cache evictions, it becomes overwhelming, and you can have a very you can have a degradation in performance. And then all I want to talk about is, when we look at the more optimized approach, what we're trying to show is that you only have to have one or two streams, and we can just load that. Once you load that, it's constantly just processing everything very quickly and very efficiently, because once the CPU knows that this is all predictable, and it knows the streams that if it knows the streams that are predictable, then it automatically does not need to explore. It can store, just use one stream alone in order to find the offsets of the other. It can be very, very effective that way. So we'll talk a lot about all of this, and there are methods in which we can figure out how whether your stream is actually working or not, and we'll do that in a future video when I start to really develop the maximal operations over here. So having a good clean memory is literally the only solution to this. It's nothing more complicated than that. And that's what we're really trying to do over here. By processing each part of the computations in blocked sequential phases, we keep the number of active memory streams to a minimum, usually just one or two. The prefetcher can predict the access pattern perfectly. Its confidence stays above, a very high percentage, and we give it, that extra 3 to 5% performance boost just from this. This is such a key concept for getting performance out of modern hardware. If you're enjoying this level of detail and want to see more content that bridges the gap between software and hardware, hitting that subscribe button is the best way to let me know if you find this valuable. Okay, so now we've seen the problem and the disastrous consequences of a bad memory layout. Now for the fun part, in part 3, we're going to build our elegant solution from the ground up. This isn't about applying a bunch of disconnected hacks. It's about a single coherent strategy that I call a perfect memory pipeline. And let's dive in. So here's the key insight that makes everything else possible. The entire solution boils down to the combination of two simple concepts: bump allocation and offset management. I spoke about bump allocation in my previous video of how memory alignment is such an important factor for parallel processing and other cool stuff. But have a look at that, because we're building on what we presented last week. And also you can check out the GitHub repository, which shows the code of how the structure of a modern LLM would be if you had to design everything from first principles. And our truly optimized struct, which we'll look at next, uses offset instead of pointers, for instance, which is an O1 access to any tensor. Then the bump allocator ensures that our memory layout perfectly matches the computation order. And this diagram shows it all. The struct on the left maps directly to a sequential memory layout, and in the middle, it enables we see the perfect memory layout, which enables a perfectly cache-friendly and prefetch-ready access pattern that results in massive speedups. And that's all we're trying to do. We're just organizing memory cleanly. It's nothing more complicated than that. I mean, it is complicated, but there's a simple solution to it. And this is the code. You can have a look at it, the GitHub repository, where everything is kind of like, already present. It's already there in version 0.1 tag. I'll share the link again below in the description. So before we dive into the complex details of the execution flow, I want to just quickly recap our core data structure, the truly optimal layer. Everything we're about to discuss is built on top of this simple but powerful design. The first and most important thing to notice here is that what's missing. There's no pointers. A traditional approach would be used to use float for every tensor, leading to scattered memory allocations. Instead, what we're doing over here is storing offsets. And this could be things like, we're storing an offset of, say, this is at 150 address, offset might be, say the base address is at 0. And then from 0, we can add, say, 153 for getting, the embedding offset. Then we can, maybe for the QKV offset weights, we can get, 153. It might be 155. It might be 157. It might be 159. We're just storing numbers. Basically, these are just offsets from the base pointer. We only store a base pointer, and everything else is just offsets. Now, these members are our table of content. For a single layer, each offset tells us the precise location of a tensor, the weights, the biases, the activations, and all the intermediate results within the single massive contiguous memory block. We're allocated for this model. This design gives us an instant O1 access to any piece of data simply by adding the offset to our memory block's base address. More importantly, it guarantees that all the data needed for one layer is packed together sequentially. This is the key to achieving the perfect cache locality and predictable memory access patterns that the hardware needs to perform at its best. So keep this offset-based structure in mind. It's a simple idea that unlocks all the complex performance gains we're about to break down. So how do we populate the offset in that structure? With a simple bump allocator, which is also there in the code, please have a look at our GitHub repository of what the bump allocator actually does. The bump allocator is cache aligned offsets. Very important concept over here. but use my code the way you want it. We start with the offset of 0. Every time we need to allocate a tensor, we call a bump. Simply takes the current offset, ensures it aligned to a cache boundary, and then bumps it forward by size. And the bump is very simple. You're not wasting memory over here, right? Because as I mentioned, for a cache alignment, you're looking at 64 bytes. So an alignment is just going to be within that 64 bytes somewhere. So you're not wasting memory especially when these models are in GBs or in TBs. So you're just offsetting a byte here. Sure, you can say a byte might add up here and there, but it's not. Believe me, you're not wasting too much memory by being cache aligned. And simply takes the current offset, ensures aligned to the cache boundary, and then bumps it forward by the size of the tensor. Now this visualization at the bottom shows how this creates a perfect sequential slab in memory. And I've also spoken about this in my previous video, which has some little animations. Highly recommend you go check that out. And this creates a perfect sequential slab layout in memory, exactly matching our computation order. And this layout creates a memory access pattern that the hardware prefetcher can predict perfectly. As we mentioned earlier, the problem is that if it cannot predict the prefetcher, it has a problem. But now once we know the sequential understanding of how our memory is laid out, how everything is just an offset, the prefetcher is not at all stressed because it knows how to predict this. And its prediction is just basically say add 5, add 5, add 5, add 5, and it'll always get the next value for that particular array in some shape or form. Once we get into the actual general matrix multiplication, you'll realize that how all of this actually all connects the dots, which will be in my next video of really focusing on the mathematical operations at its fundamental level using HPC concepts. And this layout creates a memory access pattern that the hardware prefetcher can predict perfectly, as I mentioned. And if this, and as I mentioned, if you find this really helpful, highly recommend you, to just like this button, and kind of like help my channel. Thank you. And the direct result of that bump allocation is the sequence processing pipeline. The data flows seamlessly through the transformer layer. The output from layer norm is physically located right next to the memory region of the attention step. And the output of the next region, is for the projection and so on. So, you can say that the output over here is, the input for this one and vice versa. So you're kind of like going from 1 to 2 to 3 to 4. And I've already spoken about this in my previous videos. So I'm just going to like skim through this a little quickly. And as the memory access pattern shows, we just move from offset 0 to offset X to offset Y, a simple, predictable, and incredibly crash-friendly flow. And that's what we're trying to aim over here. So let's drill down into the specific demanding computation to see this in action in the query key dot product or the Q key transpose. The actual computation requires taking a row from the matrix from the Q matrix and performing a dot product with a column from the K matrix. Now because our data is laid out sequentially, the CPU accesses the row of Q and the columns of K in a simple linear fashion. We can see that in the code how we get pointers to our Q and K vectors simply by adding our pre-calculated offsets to the base address. This approach is perfect for cache prefetching. We're just adding these layers. So this is perfect for bump allocation and cache prefetching. Now the visualization makes the benefits even clearer. We multiply the Q matrix by the K transpose matrix to get our QK transpose. Now because of our layout, the memory access pattern is perfectly sequential. We access row 0 of Q, then column 0 of KT, and then the row of 1Q, then the column of K transpose, and so on and so on. And this is ideal scenario for the hardware. It allows for perfect prefetching, keeping the CPU's execution units fully fed with data and never having to stall while waiting for memory, because all the QKB of this particular is all in memory, is contiguous for that same layer. It's very sequential. It's just going to perform this very much more easily than jumping around, not knowing what to do. And lastly, let's go to the part 4 where we'll build our elegant solution, the perfect memory pipeline. Now we're going to push it further by looking at advanced techniques for scaling the solution on real world hardware. So what we talked about was perfect alignment. We spoke about the explosion that could happen with your prefetchers if you do not have, if you're asking the CPU to constantly jump around against different memory layouts for a simple computation. We're kind of like minimizing all of these jumps and just kind of like squeezing every ounce of power from your CPU. And here we'll talk a little bit about NUMA and other cool stuff, just to get a kind of like feel, get a kind of close up this memory layout presentation before we get into the real hardcore parts of designing the AI from the grounds up. So in this part, As I mentioned, we just deep dive into NUMA, handle multiple CPU systems, and then we'll take a closer look at the CPU prefetcher to see exactly why a sequential layout is so powerful. So far, we've been mostly treating the CPU as one big unit. But on servers with multiple physical CPU sockets, we have what's called NUMA, which is non-uniform memory access architecture. As the diagram shows, accessing memory attached to a remote CPU is significantly slower than accessing it to a local local access. And our offset-based management system is perfect for this. We can split our single logical memory block into chunks and place the memory for layer 0 or node 0, layer 1 on node 1, and so on, ensuring data access is always fast and local. Now, this might sound complicated, but implementing this in C is surprisingly easy once you know the steps. It's around a few lines of code. First, you'll see that the libnuma, which is the library for non-uniform memory access, is to detect the system's NUMA topology. Second, you allocate your memory, but you use a function like mbind to pin specific ranges of that memory to specific NUMA nodes. And third, you launch your worker and use pthread set affinity, which is number of processes, to pin each thread to the cores on the same NUMA nodes as its data. And that's it. So yeah, basically, you detect where your NUMA topology is, you bind it to the node, and then you launch the workers so that it can fetch from there. And if you have a system with CAT, and Intel has CAT, where you can have the ability to, this is more advanced stuff, where you can have your L3 cache or the last layer cache, which they call it LLC, and you can pin regions of that cache memory into which regions your core can access. And this is a little bit more advanced stuff. When it comes to memory, everything is advanced, but this is even more advanced because now you're not just compartmentalizing DRAM, but you're compartmentalizing the last layer of cache, which is L3, which is shared across all the different cores. But we'll talk about that at when we at a much different a much future video. So here's something practical you can do right now. You can test your NUMA effects. You can also check out my previous heterogeneous high performance computing video, on which I've actually shown exactly how you can work with a dual socket CPU. And here are the effects without changing any code. The NUMA control command ships with every Linux distro and lets you control which CPU and memory nodes your program uses. This is actually how I recommend starting any NUMA optimization work. Run your existing code with different node bindings, measure the performance difference, and decide if the optimization effort is worth, for your specific workload. Now, the specific pitfalls that I've shown over here are the most common issues you likely encounter when working with huge pages in NUMA. These are the things to watch out for and be prepared for troubleshoot, especially the huge page allocation failure, which is often a boot time configuration issue rather than a runtime problem. So now this slide is key to understanding the mental model. At your layout time during the design phase, nothing changes. We still have one simple contiguous layout with global offsets. So now we're moving into a different NUMA, not for dual socket CPUs, but with a single socket where every core still has some NUMA access. We call it sub-NUMA, in the sense that where every core and when you have DDR memory, you can have different channels, number of channels, and each channel is generally associated with a particular core. And if you attach your data into that specific DRAM, and that DRAM has specifically attached to, say, core 1 or core 2, then you really want to put your data as close to which core is processing and computing that particular memory. And that's where we're coming over here for even a higher optimization of knowing where to store your data for that specific core so that it can compute it without changing and complicating the whole design. That's what we're trying to achieve over here. And during the design phase, nothing changes. We still have one simple contiguous layout with global offsets. So that offset strategy that we worked on, that still stays the same. What we're going to do is during the runtime, we create separate physical memory arenas for each NUMA node. So now we basically say, for this particular memory, we say that, say layer 1 offset so-and-so from 0 to 199 or whatever be it. We're going to bind this to this physical address, because every address that you allocate is all virtual address, which then needs to be mapped to a physical address. And the operating system takes care of it. And all they're saying right now, for this onwards, attach this to this particular physical address, which is now associated in channel 1, DRAM 1, for core 1, whatever be it. That's what you're controlling at the runtime. So the physical address allocation is what you control at your C level, but then you can ask the NUMA to now say where of that physical address where you want to store in that, where in that virtual address you want to store in the physical address. This is all stored in virtual address. All offsets are virtual, identical for every thread. And that's what I want to show you. This is the mapping from virtual to now physical. Is really what we're trying to, kind of like do. So the same global offsets, but different physical memory. And this mapping is also there in the TLB, which we have spoken about in the previous videos. But they now point to different data in the physical memory location that are local to the processing core. It's the best of both worlds, simple logic and high performance. So you have a simple logic at the high level, but you have the high performance because now you're associating the physical address to that specific core, but you're allocating from a readability standpoint, the virtual address just looks all contiguous. So now let's zoom back in from the system level to a very fine-grained detail. Even with our great layout, there's a potential for false sharing where a single 64-byte cache line contains the end of each token's data and the beginning of the next. If two different cores are working on those two adjacent tokens, they'll constantly fight over that shared cache line. And the solution is simple. We pad each token's embedding size up to meet the nearest multiple of 64 bytes. This might add 2 to 5% memory overhead, but it guarantees perfect isolation between tokens and eliminates the last source of false sharing. So all we're trying to do is that, one of the things with high performance compute is what I'm trying to present is that memory is cheaper than buying 10,000 GPUs. This is where the whole concept is coming. So I'm willing to sacrifice and use more memory, a little bit more memory, because that cost is still much cheaper than using and buying GPUs. That's where this whole concept is coming. So we're willing to sacrifice a little bit more of memory by having by having our cache alignments, in bumping it up, so that it's all perfectly clean, so that every token is well padded. And we're willing to do that because say a 1 TB memory, that you buy from the market might be say $11,000. A very high-end GPU is going to be costing you $40,000. So just by cost analysis, that memory is much cheaper. Just by the cost-benefit analysis. So we can use memory. That's not the bottleneck from a business standpoint. And that's where a lot of this presentation is saying that let's use memory. Let's be a little bit generous with our memory layout. It's cheaper. And based on that, giving us the freedom to say let's use our memory. And because of that, we can have cache alignments. We can pad these bytes so that everything is all about high performance compute. And from a business standpoint, the cost is much more manageable compared to buying a series of GPUs. Because we're trying to squeeze every ounce of CPU power so that what was extremely slow is now much faster. It may not be as fast as a GPU, but for the cost-benefit analysis, you can say that that underutilization and now amplifying your code and making it high performant on the CPU, makes it all the more attractive for the cost that you're spending on this. And that's where I'm giving the freedom that memory is cheap. And now let's visualize exactly why a sequential layout is so fast by looking at the CPU's prefetcher. This is a good path. The good path is basically saying, when we request data, say at 1000, and when it then asks for data at address 1064, it's all about, it's a simple pattern. It's a simple pattern detection. It's the next address is at 1064. The next cache line prefetches the data, the stride one pattern, and it's constantly been able to speculate when the next thing is. And that's really where we were talking about, the explosion is that we're not jumping around. Everything is clean in memory. It knows the offset. Everything is an offset, and the offset is predictable. And once the offset is predictable, it knows to do this prefetching automatically. And we're constantly getting fast cache hits. And when we get fast cache hits, we get a good pipeline of efficiency. And then let's look at this in contrast over here. So the bad path, in contrast, is basically when you don't consider all the details of the memory. The request data at address 1000, then it jumps to 80,000 because now from layer 1 QKV is over here, and then the layer norm is at a completely different address, because in between this part, even though they're all contiguous in memory, they're the storage of data is not contiguous. So you have all the QKV of all the layers over here, then you have all the layer norms of all the layers over here. So they're constantly jumping rather than them being sequential in terms of execution, not just in terms of grouping them in pace of operation. And the prefetch is completely confused. It has no pattern to follow. This leads to continuous cache misses, and the compute unit spends more time of the idle time waiting for data, because now it's jumping from 1000 to 8000, and from 8000 to something from 2000, and it's constant. And then you eventually stall, and then it just just reduces. You're stalling the processor, and we're talking about 2.4 gigahertz, so you may not necessarily feel it, but when you have an algorithm that's in GBs, the CPU can be insanely slow because it's not hyper optimized. So the core principle is this: the CPU prefetcher is essentially a pattern recognition engine that runs in hardware. It's like a chess grandmaster. It can see many moves ahead if the pattern is clear, but it struggles with chaos. Our job as a prefetcher engineer is to create simple, predictable patterns that has left the hardware to shine. The difference is stark. A sequential layout leads to a very high percentage. It can be utilization, 90 to 95% utilization. We can easily monitor this through benchmarks, which we will show shortly in my future videos. And while an interleaved layout can drop you to around 40% to 60% memory wait time, this is where our 3 to 5x speedup comes from. And we're talking about specifically about CPU. We're not saying that CPU is better than GPU or anything of that sort. We're talking about how can we hyper optimize the code on CPUs and why are we not doing that. That's what this is all about. And this is where I just want to kind of like show you, from a mathematical standpoint of, because these things are all computer science theory. And yes, there are real world obstacles out here, but for the most part, when you have a very good cache hit, when you have good TLB hits, TLB is basically where you have your virtual address to physical address mapping. And then we know it's all sequential because it's all based on the offsets. The prefetcher is also, very, very clean over here. It's constantly able to predict the patterns and it's having minimum explosions over here. You're looking at a decent performance at every part of this whole process, which you can show that, if it's all bouncing around, then your caches are going to have cache misses. And because of the cache misses, you're going to have a reduction. That's what we're really looking at, and these are all going to have cache hits. Whereas here you can have a higher you can have a higher cache hit, you can have a much higher TLB hit, you can have a much higher prefetcher hit, and all of these accumulations can give you much higher performance on the CPU itself. And that's what we're trying to aim over here, and that's what this presentation is all about. So after all that deep dive technical work, the offset management, the NUMA awareness, the cache line padding, and the prefetch analysis, what does this final pay off? This is what we get at the end of it. This slide summarizes the incredible performance benefits with our cache optimal approach. We're not just getting small incremental gains, we're fundamentally changing the performance characteristics of this application. We see in our cache hit rates to over, say around 95% compared to 60% in a traditional interleaved layout. And the prefetcher accuracy also hits very high percentage, and because we have designed perfectly predictable memory access patterns. And our TLB hit rate is also very high thanks to our use of huge pages and sequential access. The comparison at the bottom makes it crystal clear. We go from a traditional approach that is memory bound with random access where the CPU is constantly waiting for data, and we move to our own optimized approach that is cache optimal with sequential access where each part of the memory hierarchy works in perfect harmony. And the final result, every increase in optimization at every part of the whole CPU process, gives us that 1%, 1%. But there's so many of these 1% improvements that overall it can give you a much higher speed and much more better utilization of your CPU. And this is the power of the hardware-aware software design. We've transformed a memory-bound problem into a compute-bound one, and we've unlocked the true potential of the CPU. All right, that wraps up this part of the series. What we've built here is more than just a memory strategy, it's a mindset. We now have a full overview of how to organize our AI project from the first principles. So now we're no longer being randomly creative in our code structure. Instead, the creativity shifts to where it matters: HPC design, memory efficiency, and sequencing every ounce of power from that CPU. And honestly, for me, this looks beautiful. Go check out the GitHub repository. It shows the bump allocation and all that cool stuff. So it's on 0.1 version of my Git repo. The bump allocator, the offset tables, everything we've talked about is there in code. I'll be improving it over time, but this already sets up a solid foundation for building a GPT-2 like transformer in pure C. Now it opens the door for more advanced architecture like mixture of experts, which we'll talk about in a much more future video. But first, we're going to take everything we've learned here and dive into beating the heart of the modern AI in the next video, which is the GEMM, which is a general matrix multiplication. And this is more complex than one can ever think of how we actually do everything in a much more highly optimized level, because once we master the matrix multiplication, which is the heart of all modern AI, where we understand everything about the AI, and at least where we're solving the biggest bottleneck. And we break it down, optimize it, and show how all these memory layouts ideas plug directly into high performance compute. If this kind of low level AI engineering is exciting to you, hit that like button, subscribe, and let's keep going on this journey. And let's build our AI from first principle. And until next time, please take care. Thank you.